So remember, a very quick way to know if something's a function or not when you have a picture is the vertical line test. So we said if you draw a vertical line and it only touches the graph once, that's good. It's a function. So if you look at this crazy squiggly picture on the left there, any place where I draw a vertical line, it's only going to touch the graph once, okay? So this we would say, yes, it's a function. Then remember, if we want to know if its inverse would be a function, it would have to pass the horizontal line test. This definitely does not pass the horizontal line test. If I start to draw a horizontal line, it's already touched the graph twice at this point, okay? Sometimes it might touch it like 6 times. The point is it can't touch it more than once, or it means its inverse is not going to be a function. So would its inverse be a function? No. The next one fails the vertical line test. It touches the graph more than once if I draw a vertical line. So is it a function? No. However, its inverse would be because it passes the horizontal line test. Anytime you draw a horizontal line, it only touches the graph once. So even though it's not a function, its inverse would be. And then the last one, it's a function and its inverse is a function because it passes the vertical line test. Anywhere I draw a vertical line is only going to touch the graph once. And it also passes the horizontal line test. Anywhere I draw a horizontal line, it's only going to touch the graph once. So we say, yes, it's a function. And yes, its inverse is also a function. And then we had one to practice where we find the inverse. Remember when you want to find the inverse that we usually switch the x and the y? So you might want to write it with like y equals instead of function notation. And then, normally we switch x and y. It's t and y this time. That's fine. Just you have to switch them still, okay? So, and then we solve for y, we learned yesterday. So remember, when you're solving for a variable, you're working backwards till that variable is alone, which means essentially PEMDAS in reverse. So if there were any addition or subtraction, we would do that first, but there's not. There's multiplication. So we could divide by -8/27, but it's going to be better to multiply by the reciprocal. If you remember, that's this dividing by number is the same as multiplying by its reciprocal. So we're going to multiply by -27/8 on both sides because it will equal 1 on this side. So we're going to have -27/8 times t. And then you should have taken the cube root of both sides because the cube root is the opposite of cubing something. It cancels it and just leaves it with y. Now, if you notice, if you look for this in your answer choices, you're not going to see that anywhere. That's because we have to use some of the concepts we learned earlier in this chapter. Like, remember when you have a quotient, you can think about writing that as like 2 separate things we learned. So, like, you can actually take the cube root of -27 and the cube root of 8 because those are perfect cubes. The cube root of -27 is just -3, and the cube root of 8 is just 2. Remember, the t would have to stay on the inside because if you had t to the third, like if you had a group of 3, you could take the third root, right? Because the third root and the third power would cancel. But it's only t to the first, so it would just have to stay on the inside. So now hopefully you can see this is the choice. It just, instead of y, it has the function notation, h of t. Questions on that at all? All right, we're getting into 3.5 today, which is about graphing square root and cube root functions. So before we can get into that, we need to review domain and range real quick. We've already reviewed domain a little bit in this chapter. So remind yourself, domain means the x values that are allowed in a function. So range means the y values that appear or are allowed in a function. So let's go back to thinking about y equals x squared. That's a parabola. We spent a whole chapter on those, but back in that chapter, we didn't really talk about domain and range much. So we're going to get into it now. So domain means like, what can I plug in for x? Well, you can plug in anything you want. Like, think about, could you square a negative number? Yes, like -4 squared, you can do it. It would just become +16. Can you square 0? Yes, 0 squared is 0. Can you square a positive number? Yes, like There's nothing that you can't square, okay? So since there's no restrictions on x, that's when the domain is all real numbers. And remember, in interval notation, you write negative infinity to positive infinity with those or open brackets around the end, okay? Another way to think of it is if you just think about the ordered pairs on your graph. Now, this is a really rough sketch graph, okay? Like, think about if you did 2 squared. The output would be 4, okay? So maybe I'll even redraw this a little bit real quick so that it's just a little bit more accurate. 2 squared is 4, and negative 2 squared is also 4. So here's what it would kind of look like, okay? But here's the thing. Again, we have like the point negative, not negative 2, I didn't mean that, 2, 4 on the graph, and you also have negative 2. Like, I want you to focus on the x's. They can be positive or negative, okay? That's why the domain is going to be all real numbers. Now I want you to focus on the y's, though. Remember, when you square a positive number, you get a positive because 2 times 2 is 4. But when you square a negative, you also get a positive. Like, can you guys see that there are no negative y values on this graph ever? Do you see that? So that's why our range is just going to be 0 to infinity. You're not going to have negatives, okay? Remember, you have to have that, what we call a closed bracket around 0, because we do have the y value of 0, right? Like, if you do 0 squared, then it's 0. So both graphs have 0 on them. It's just that the x's also have negatives and the y's don't. Another way to think of it is there's no points down here in quadrant 3 and 4 where the y's are negative, okay? So that you can't have negatives for our y values or the range. What if we did x to the power of 3 instead? Well, you can still plug in anything you want. Like, you can do a negative number to the 3rd power, positive, 0, okay? Notice if you do plug in 0, 0 to the 3rd is 0. Like, we're still going to have both graphs we looked at so far had the point 0, 0. Now, so once again, the domain is going to be negative infinity to infinity. There's no restrictions on x. This time there's no restrictions on y either, because if you, let's say if you did like 2 to the 3rd power, like if I plug in 2, I'm going to get 8 as an output. If I plug, now again, I know that doesn't look like we see the 0.28 on our graph. It's because it's a really rough sketch of it, okay? But then like negative 2 cubed would be negative 8. So like you'd have the point negative 2, negative 8. So like, look, we have positive x's and negative x's this time. We have positive y's and negative y's. There's no restrictions on the domain or range. They're both all real numbers. They're both going to be negative infinity to positive infinity, okay? Because there's no restrictions at all. Let's look at the square root of x. So I want you to think about 0, 0 would be kind of like the starting point of this graph, because if I plug in 0 and take the square root, I'm going to get an output of 0. I can't take the square root of a negative number this time. Like, that's why there's no points over here for the x, because like the square root of negative 25, that doesn't work. It can't be 5 because 5 times 5 is 25. It can't be negative 5 because negative 5 times negative 5 is 25, not negative 25. Like, remember how you get imaginary numbers if you take the square root of a negative. So this time the domain is restricted because we can't take the square root of a negative number. X can't be negative. You can't fill in a negative number. 0 is the smallest thing you could plug in, and then any positive number after that, like toward infinity. So you'll write it like that. So the range will actually be the same thing. Guys, a great way to think of it is, look, the whole graph for this one is in quadrant 1, where x and y are both positive. Like, there's no points over here where x is negative. There's no points down here where x and y are negative. There's no points over here. The whole thing, like, the x's have to be 0 and greater, and so do the y's. So the domain and range are going to be 0 to infinity if you're looking at the square root of x, okay? Now, if it were the cube root of x, that's totally different. There's not going to be any restrictions this time. because cube root, you can take the cube root of a negative number. Like, let's think about an example. The cube root of -8 is just going to be -2. You can do it this time, because like, think about -2 times -2 is 4, but then times -2 again gives you -8 back. So we can plug in for x positives or negatives or 0. Like, again, notice the graph has the point 0, 0, because if you take the cube root of 0, it's still going to be 0. So there's no restrictions on what you can plug in for x. There's also no restrictions on what you can get as the output. Like, this graph would have the point 8, 2 on it. Again, this is a rough sketch, so it doesn't look very good from the picture, but it would have the point 8, 2, and then it would have the point -8, -2. Like, the x's can be positive or negative, so can the y's. There's no restrictions. It's all real numbers for domain and range. So now that we've reviewed domain and range a little bit, we're going to start to be making some graphs ourselves, but we're going to talk real quick. So we're going to be looking at square root graphs and cube root graphs today. We've looked at them a little bit already, but we're going to have this slide as kind of a nice summary. If we graph just the square root of x, like, eventually, guys, there might be like a number here or a number here. So when there's no extra numbers like that, we call it the parent function, okay? Now, I want you to think about like how this graph was created. We'd have to just take x values and fill them in and make like a little xy table. Like, if I have y equals the square root of x, if I plug in 0, the square root of 0 is going to be 0, right? If I plug in 1, the square root of 1 is going to be 1. So you're going to see both of those points on the graph, okay? Notice 0, 0, again, I want you to think of it sort of as like the starting point when you're doing the square root of x, because you can't take the square root of a negative, right? 0 is the lowest thing you could take this square root of. So I want you to maybe circle this. We already talked about it once, but the domain has to be things 0 and higher. You can't take the square root of a negative, okay? That's why it says x is greater than or equal to 0. We wrote it like this. It's the same thing if you say x is greater than or equal to 0, okay? But then same for y. You can't have negatives, okay? Again, one more time, we wrote it like this. If you say y is greater than or equal to 0, that's the same thing as when we write it that way in interval notation, okay? Then cube root, I want you again to think about, where did this graph come from? You'd have to make a table of values first by plugging in different things for x and y. And I want us to know the point 0, 0 is always going to be there when you have the cube root, of a function. Again, that might change if you have like a +5 or something like that. But when it's what we call the parent function, where there's nothing added or subtracted or multiplied, just plain cube root of x, nothing else, it's always going to have the point 0, 0 on it, okay? Then if you take the cube root of 1, that's going to be 1. The cube root of -1 is going to be -1. So you'll notice that you see both of those on your graph as well, okay? But a lot of times we're going to start by thinking about the point 0, 0 on both graphs. They both contain, the parent functions both contain those points, because the square root of 0 is 0 and the cube root of 0 is 0, okay? And then remember, with cube root, like we already said, domain and range are going to be all real numbers. So what we're going to be looking at now is we're going to compare, like, remember the parent function just looks like this, cube root of x. How would that, we just looked at the graph of that on the last slide, how would it compare to 4 times the cube root of x? Well, the first thing we're going to, again, this is called the parent function when it's just like plain old cube root of x, okay? If I want to know how this compares to this, one thing we could do is put them both in our graphing calculator at the same time. So I want you to go to y equals. Guys, if we want to do the cube root of x, remember, you could just do x raised to the power of 1/3 if you want. Remember how that's the same thing as the cube root of x? Also, if you don't know this yet, I'm going to show you where to find the cube root button on your calculator. If you hit the math button, it's the fourth thing in the menu, okay? It'll give you a cube root. So again, you have two options how to type it in. You can do the math button, or you can just do x to the 1/3 power, because it's the same thing. We want to know, how's that compare to if we have 4 times the cube root of x. Okay, so pay attention to my color codes here. The parent function is going to get graphed in blue, and then 4 times that thing will be in red when I hit graph. So look, the blue one is the parent function. Do you see how the red one kind of got like stretched vertically? Do you guys see that? That's what's going to happen when you multiply by a number that's greater than 0. So that 4 did that, okay? If it were like a 5 or a 6 or a 7, it's going to stretch it even further, okay? So I'm going to clear the parent function out, because we're going to now make a picture of 4 times the cube root of x. So what we're going to do is go to our table, and remember, I want you to make sure the point 0, 0 is in your table, and then we're going to copy a point on each side of it, a couple of points, okay? Technically, you need a minimum of 3 points. I definitely want 0, 0 to be in your table. We're going to put that kind of in the middle every time. And then again, this one, we have a table with several values we're just going to go ahead and fill in. So I'm just copying these right out of you should have your table up on your screen, so on your calculator. We're just going to copy it. When you see -3, it's around -5.8. Then at -2, it's like -5.04, -1, -4. Again, we're just copying it right out of the table. We got a round because some of these go on for quite a few places, so it'll just be an estimate. Again, 0, 0 is going to be on our graph a lot of times, okay? And then we've got -1, -4, and +1, +4. And then we've got -2, -5.0, and -3, -5.8. So that's just a little further down. We've got 2 and 5.04 and 3 and 5.8. And then look at your calculator screen to see how to sort of connect it, but it looks something sort of like this, okay? Again, if we drew the parent function at the same time, you saw that it looks like this. Like my purple one is more stretched out. So let's add that to the right. I never actually wrote down the answer. We say that it stretches it out vertically. Okay, and then we're going to do domain and range. So for a cube root function, the domain and range are both going to be all real numbers. Look at your table to help you. See how there's negative x's and positive x's and zeros. Like there's no restrictions. You can have any real number. Same thing with y. There's negatives, there's positives, there's 0, there's no restrictions. So the domain and range are both going to be all real numbers, which remember we say -infinity to infinity in interval notation, okay? Again, I would be fine with you just writing all real numbers. That would be okay with me. But like I told you before, interval notation is especially important if you're going to go on to pre-calc, okay? So that's a cube root. We're going to look at a square root now. So again, if this weren't there, we call that the parent function. Our first question is going to be, how does the parent function compare to 1/4 square root of x? So let's actually, again, this is the parent function. How do they compare? Let's, again, go ahead and graph them both at the same time. Let's put the parent function into y1, so just the square root of x. And then we have 1/4 times the square root of x. Guys, I like to do my fractions sideways. I know some of you type them vertically. Sideways will actually be more helpful because it will give us decimals when we look at our table. Fractions aren't going to be very helpful because those are harder to graph. So you might want to type your fraction, your 1/4 sideways, Or you could even do 1 divided by 4 and just put 0.25 if you want to, okay? So again, when I hit graph, keep in mind it's going to graph the parent function in blue and the new one in red. See how it like shrunk it down this time? Remember how the last one stretched it out. So this, what's going to happen is if this number right here is greater than 1, it's going to stretch it out. If it's between 0 and 1, like 1/4 or 1/2 or 0.7, anything that is between 0 and 1 is going to shrink it vertically. Okay. So again, if we want to make a graph, we're going to have to write down what points to put on our graph first. So if you go back to y equals again, I'm going to clear out the parent function because we're actually just going to graph 1/4 square root of x. Notice there's lots of errors here because remember, you can't take the square root of a negative number. 0 is the first thing that you could ever plug in here, right? Like if you take the square root of 0, that's 0, and then 0 times 1/4 is still 0, okay? So that's where our table is going to start. When it's square root, you can't take the square root of a negative. And then we'll just copy the other values when x is 1, y is 0.25, and so on. Really, you just need technically at least 2 when it says square root, but we'll graph a couple points on this first one. So again, remember the function shrunk. So these points are going to be so hard to graph because they're just these tiny little decimals. And it's even harder on the smart board. So forgive me because yours is probably going to look nicer than mine. So remember, guys, you're only going to draw like an arrow one way this time. Like the graph doesn't go down here into the negatives. You can't take the square root of like 0, 0 is your start point. So when we don't do domain and range, they're both going to start at 0 and go toward infinity, but there's no negative x's and there's no negative y's. So they're both going to start at 0 and go toward infinity forever. Okay. Questions so far at all? Okay, so since this next slide is already written in on your handout for you, I would just look up here and make sure you're paying close attention. You probably won't have to add anything because all the information is there for you. So far we've taken the square root of x or the cube root of x, and we looked at what happened when we put a number here in front. So we said when that was, remember when it was 4, how it stretched the graph out? That's always going to happen. When a is greater than 0, that number in front of the radical, it's going to stretch it. When it's between 0 and 1, like the 1/4 or 0.25 that we looked at, it's going to shrink it. If it were negative, it would flip it over. We should be familiar with that already back from chapter 1. Do you guys remember when we graphed parabolas and they opened upward if a was positive, but then if it were negative, it flipped it? Remember that? So it's the same idea. It's if a is negative, it's going to flip it, okay? Now we're going to look at what would happen if there was something like added or subtracted to the x underneath the root. That's going to take our graph and it's going to either shift it to the right or left, okay? If h is positive, it's going to shift our graph to the right. So like what could happen is this graph that I just graphed here, if this went on further and it had like a -3, you have to be careful because minus is the formula. So 3 is actually, it would like shift it to the right 3. So instead of starting at 0, 0, it would start at 3, 0 instead if that happened, okay? The graph can also get shifted up or down. If you had something out here, it would shift it up 3 units. So it would take our graph that we already did and it would look like that instead then, okay? So that's kind of summarizing that stuff for you here. If you look at h, the number that's added or subtracted on the inside, like to the x, okay, it's going to shift it left or right. K, do you see how like it's on the outside? It's not, I'm going to clear this ink, like the root stops here, right? Like K is on the outside. The number on the outside will either move the graph up or down. Up if it's positive, down if it's negative, okay? So knowing all this information, we're going to try to predict what would this look like compared to the parent function, like plain old square root of x. How would they compare? We're going to try to predict it before we even graph it in our calculator, okay? So I'm going to write the general formula. Remember how, like, I'm just copying it from the last slide. Y equals a times the square root of x minus h, and then plus k. So let's pay attention to A first. The 2 would stretch it out vertically, like it's going to be a vertical stretch. But because it's negative, it's also going to flip it upside down. Okay, now let's look at this number next, which is h. So h, you have to be careful, guys. It's positive 3. A lot of, what's up? Okay, so again, what I was starting to say is sometimes people look at this and they think h is going to be negative 3, but you have to remember that the formula has a minus sign. So h is kind of like the number after the minus sign. It's positive 3. So what that's going to do is it's going to shift the graph to the right 3 units. Okay, and then k equals 2. So what that's going to do is it's going to shift it up 2 units, okay? So remember, I'm going to sketch the parent function real quick. Remember how it normally starts at 0, 0, like the square root of 0 is 0? That point 0, 0 is going to get shifted to the right 3 and up 2. Like the graph would kind of look like this now instead, except it's also going to be flipped over because of the negative 2, okay? So let's do this. Let's go to y equals again. First thing, I'm going to have us graph them both at the same time again. So let's graph the parent function, the square root of x, and then our new function. Guys, when you type this in, you have to be very careful, okay? Do it with me. We have negative 2, and then the square root of x minus 3. Some of the older calculators have parentheses when you type a square root. You would need to close the parentheses if yours has that, okay? Mine does not. But then this is the most important thing. You have to arrow out of that because the plus 2 is on the outside of the root. We don't want it to be on the inside because that's supposed to shift it up 2 units. If you accidentally put it on the inside, that's just going to make it go right or left more, okay? So the 3 on the inside moves it to the right 3, and the 2 on the outside moves it up. The number on the inside moves it right or left. The outside moves it up or down. So when we graph it, I want you guys to look at the blue one. That's the parent function. I want you to pay attention to 0, 0. Again, do you see what happened? I'm actually going to, I have it graphed on my paper. I'm going to pull that up real quick just because I want to be able to write on it. So the parent function has the point 0, 0. What happens is that point goes to the right 3 and up 2. So this point right here is like the new starting point of our graph now, okay? And then from there, it's flipped upside down now because of the negative 2, okay? So when we go to make our table of values, so you don't have a graph on your paper, we're getting to that now. So we're just going to be graphing this one. We're not going to graph the parent function. So let's maybe go back to y equals and clear out the parent function. We're just going to graph the new one. But again, it doesn't start at 0, 0 anymore. So like if you go to your table, there's going to be error at 0 this time. Usually you can take the square root of 0. Think about why we wouldn't be able to do that this time, guys, because look, if I plug in 0 in place of x, 0 minus 3 is negative 3. You can't take the square root of a negative number. So I also can't plug in 1 because 1 minus 3 is negative 2. You can't take the square root of a negative. 3 is the first thing you can plug in this time because 3 minus 3 is 0, and you can take the square root of 0. That's why when you look at your table, the first point that kind of works is 3, 2. That's like the starting point of your graph. And then 4, 0. We need at least 2 points, okay? So I want you to write down 3, 2 and 4, 0. Now, again, guys, I really want to stress to you, we should technically be able to find this point right here without our fancy calculator, because we need to understand that it just took 0, 0 and moved it to the right 3 and up 2 because H is 3 and K is 2, okay? So like when you do your edge elastic later, you might want to see if you can figure this point out by yourself, but then feel free to look at your calculator table to help you, okay? But 3, 2 is kind of like the start of our graph now, and then 4, 0 is our second point, and then we'll kind of connect it. Remember, it only goes in one direction. Like, don't do that or something because it doesn't go past the point 3, 2. That's our start point, okay? So then domain and range. Domain, remember, is the x value. So let's think about this for a second. 3 is the smallest thing we'll ever have on for our x's, right? Like remember, we can't plug in 0 this time because it's an error. We still can't plug in negatives like normal. 3 is the smallest thing we can ever input into the function. So 3, and then from there it goes up forever toward infinity. So you're going to say, one way to say it would be x has to be greater than or equal to 3. But in interval notation, you would say 3 to infinity, okay? Now, the range is going to be a little tricky because the graph is flipped this time. Remember, the parent function, the range just goes from 0 to infinity. Well, this time, the highest y value we ever have on our graph is 2, but then it's going down because the graph is flipped, right? Like if you confirm it by looking at the table on your calculator, 2 is the highest y, and then it goes down toward negative infinity. So we have to be careful the order we write it in because negative infinity is small and 2 is the biggest. So like negative infinity would come first. So your y's, again, one way to say it would be y is less than or equal to 2. So another way would be negative infinity to 2. Remember, you want your closed bracket because 2 is included, right? Like, look right there. 2 is one of our y values on our graph, but then it's anything less than that. It goes to negative infinity, okay? Questions on that one at all? Okay, and then we're going to try 1 cube root. Again, guys, I want you to try and think about if we had the normal parent function, how would it compare to this? Let's take it piece by piece. I'm going to write out the formula like this because we want to remember, what does A do to the graph? So A is either going to stretch it or shrink it. Since 3 is greater than 1, remember, any number greater than 1 is going to stretch it vertically. So since A is 3, it's going to be a vertical stretch. It's not going to flip upside down this time because A is not negative, it's positive. So then H is -4. Again, you have to be careful because it looks positive, but remember how the formula has a minus, but see the plus? The only way a minus could turn into a plus is if this were a -4. Minus a -4 would make it turn into plus. That's how I know it's -4. What that's going to do is it's going to shift the graph to the left 4 units. Okay, and then K is -1. So it's going to shift the graph down 1 unit. So remember how the normal function, if we plug in 0, we get 0. Like the square root of x and the cube root of x normally have the point 0, 0. So what's going to happen is 0, 0 is going to get shifted to the left 4 and down 1 because all the points are going to get shifted to the left 4 and down 1, okay? So again, we should kind of be able to understand that the point -4, -1 is going to be on our graph before we even put it into our y equals, okay? But then you can use your fancy calculator to help you, okay? So again, I already have them graphed both for you here. The red one is the parent function, like plain old cube root of x. So it's going to stretch it out, and it's going to shift every point to the left 4 and down 1. Okay, so like there would be the new point. So we'll just go ahead and graph the new function in y equals. So again, be careful how you type it in. We have -2, or I'm sorry, that was the last one, 3 times cube root of x plus 4. So again, you can go math and choose number 4 and make sure x plus 4 is under here. And then make sure you arrow over to get out of it before you type your -1. Another way to type it in would be to do like x plus 4 to the power of 1/3, right? Remember, taking the square root or the cube root is the same thing as to the 1/3 power, and then like that. Like those are the same thing, okay? So take a look at your graph. It looks like what I already showed you on the paper, okay? Now, if we look at our table, now I want to go back to this one real quick, guys. When you're doing a square root, you kind of only need 2 points because like a starting point and then another, so you know what direction to draw your graph, okay? When it's cube root, I really want 3 points. Like normally we would have 0, 0, 1, 1, and 1, -1, right? Because it goes on forever both ways. But now -4, -1 is your center instead. So when you go to your table, I just want you to give me, like, think of this as being your center point, -4, -1, and just give me 1 point below it and 1 point above, just to help us connect it well, okay? You could always do more points than that if you want, but I just want at least 3 when it's a cube root function, okay? So then you would go ahead and graph it on your paper. So again, mine's already graphed, but here's -5, -4, -4, -1, and then -3, 2, so that we can see how to connect it, okay? And then, guys, remember, the domain and range for cube root are always going to be all real numbers. Remember, square root that we just did on the last slide was restricted because you can't take the square root of negatives, but you can take the cube root of negatives. Remember, another way to know is look at your table. Look at the x's. There's no errors in the y column, right? That's good. That means you can plug in negatives and positives, and the y's can give you an output of negative and positive. Like there's no restrictions. It's all real numbers. So you're going to write your -infinity to infinity for both. That was not a very good infinity sign. Let's just fix that real quick. Bless you.